these are my contents. Let first of all know the definition and array notation of permutation groups. A permutation of a set A is a function from A to A that is both 1 to 1 and onto. Since there are altogether n factorial permutations on n objects, and this is the array notation of permutation groups, that let A is equal to transposition 1, 2, 3, 4. Example, a set of all permutations on 1, 2, 3 is called the symmetric group on 3 letters denoted by S3. There are 6 permutations possible, that is 3 factorial, where in a transposition the upper letters are called as domain and lower are called as range, where here we are getting 6 permutations possible in S3 group. The permutation in S3 group is transposition 1, 2, 3. Here I am keeping the domain as a constant everywhere. We can keep domain as constant or range as constant as per our convenient. That is, here the permutations of transposition 1, 2, 3 are the first A is equal to 1, 2, 3 is one permutation, 2, 3, 1 is another one permutation, 3, 1, 2 is one permutation, and 1, 3, 2 is one permutation, and 2, 1, 3 is one permutation, and 3, 2, 1 is one permutation. Here we are getting the total 6 permutations in S3 group. And identity permutation, that is A is equal to transposition 1, 2, 3, 4, 5, 6, so on up to n, is A is equal to, here the range, the domain and range are same. In a transposition where the domain and range are same, these transformation are called as identity permutation. In other words, it doesn't change anything. In previous slide we can get the A is equal to 1, 2, 3 and 1, 2, 3. This is the identity permutation. And symmetry of square D4. Here we can see the R0 and R360. R360 is equal to, the square is like this, that is 1, 2, 3, 4. This is for 0 degree and 360 degree. It doesn't change. It does not change. It remains same as where it turns into R90 degree, that is R90 degree. When it turns from here to here, it changes from 90 degree. That the square becomes in 1 comes here and 2 comes here, 3, 4. This is for 90 degree. Therefore, in place of 1 we are getting 2 here. In place of 1 we are getting 2, and in place of 2 we are getting 3. In place of 2 we are getting 3, and in place of 3 we are getting 4. In place of 3 we are getting 4, and in place of 4 we are getting 1 here. Similarly, when again the main square turns into 180 degree, it comes to 180 degree. At that time the square becomes and 1 transpose to here, that is 1, 2, 3, 4. This is for 180 degree. Similarly, as again it changes to, again this square changes to 270 degree, that is again this is for R180 degree, and R270 degree is equal to, it rotates here, that is 1 comes here, 2 comes here, 3 comes here, 4 comes here. This is for 270 degree. This is all about the symmetry of square D4. And cycle notation. A cycle notation is another one type of notation of a permutation groups, where the cycle, this is the very helpful in finding the permutation groups. That is, when finding the image of an element, we just need to find the cycle which contain it. that the element will appear once, and it is easy to find the order of the product. The advantage of the cycle notation this is, and here 1 to 3, 1 to 3, and 3 to 1, this is one cycle, and 2 to 5, 2 to 5 is one cycle, and 5 to 6, 5 to 6 is second cycle, and 6 to 2 is the third cycle in a one cycle, and the 4 to 4 is one cycle, so it it is only one cycle, and we can write it as a 1 3 and 2 5 6 and 4, and it is of order 3. Here how many transposition we are getting in one cycle, that is called as the order of the cycle notation. That is alpha is equal to, how to, let first of all let know about the how to write the cycle notation. Here 1 to 2 is 1, and 2 to 3 is 1, and 3 to 1, sorry, here I am skipping one. 4 to 4 is also a one cycle, we can represent this also, and beta is equal to 1 to 2 and 2 to 1, here it is, and 3 to 4 and 4 to 3, here two cycles, and here two cycles, we are getting here. Even and odd permutations. A permutation consists of even number of transposition. It is called as even permutation, where the even numbers we are already know that 2, 4, 6, 8, so on. These are the even permutations, and the permutation consists of odd number of transpositions. It is called as odd permutation, where we already, that is also we know that. Let's find the even or odd permutation, that A is equal to transposition 1, 3, 7. 1 and 3, that is one transposition, and 1 and 7, it is also one permutation, it is of second order. Here we are getting two transpositions, that is called, it is of order second order, and it is even permutation, and B is equal to 1 6 3 2 and 4 5 7. Here 1 to 2 is one transposition, and 1 to 3 is another permutation, and 1 to 6 is one permutation, and 4 to 5 is 1, and 4 to 7 is 1. It is of the fifth order, and it is odd permutation. Here in previous slide it is directly given question, but here it's in the direct permutation method. In this condition we have to convert these types of problems into cycle notation, and 1 1 to 2, 2 to 4, and 4 to 1, this is one transposition, and 3 to 6, and 6 to 7, and 7 to 5, and this is second permutation, and we can split into 1 to 2 1, and 1 to 4 1, and 3 to 5 1, and 3 to 6, and 3 to 7. Here we are getting 5 transpositions, so that it is called as fifth order, hence it is odd permutation. Problems. Let A is equal to 1 2 3 4, and suppose that B of 1 is equal to 3, and B of 2 is equal to 1, B of 3 is equal to 4, and B of 4 is equal to 2. It's very simple question, where let A is equal to transposition 1 2 3, this is the domain. Here 1 2 3 4, this is domain, and this is domain, and B of 1 is equal to 3, that is B of 1 is equal to 3, and B of 2 is equal to 1, B of 2 is equal to 1, and B of 3 is equal to 4, and B of 4 is equal to 2. It's simple, and here we have to find A of 2. A of 2 is equal to 1, here A of 2 is equal to 1, and A of 1 is equal to 3. And operations on permutation. Let A is equal to transposition 1, 2, 3, 4, and suppose that find let A is equal to transposition 1, 2, 3, 4, and suppose to find that A into B of 1, that is A is equal to domain 1, 2, 3, 4. The domain should be constant in A and B, and the range is changing here, that is 2, 4, 1, 3 in A and 3, 2, 4, 1 in B. A into B of 1 is equal to, always the permutation multiplies from right to left, from right to left, that is 1 1 into 3, that is 1 into 3, that is where the 3 third term is 1 and 1 is 2, so that here 2 comes, and that is A into B of 1 is equal to 1. The operations on permutation, the previous question is they are only asked, that is AB of 1, and here to find the AB, that is let A is equal to transposition 1, 2, 3, 4, and suppose to find that A into B, that is the domain is 1, 2, 3, 4, and the range is 2, 4, 3, 1, 3 for A, and B is equal to 3, 2, 4, 1. Here the always the permutation in previous slide I only told that it is always type from right to left, and 1, 3, 3 third term is 1, here 1 comes, and 2, 2, 2 to 4, so that 4 comes, and 3, 4 fourth term is 3, so that 3 comes, and 4, 1, that is fourth 1 is 2, and here 2 comes. And application, the permutation in Rubik's cube. A popular puzzle, Rubik's cube, invented in 1974, has been used to illustrate the permutation groups. Each rotation of layer of a cube results in permutation of surface colors, and it is member of a group. And in Rubik's cube, it is a contain 6 small squares of 6 faces. It is a big cube where it have 6 faces, that is 6 colors, and small 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 squares, small cubes like 9 cubes, and totally for one face we are getting 3,62,880 permutations for one face, and there are 6 faces, then totally 21,77,280 permutations are possible in Rubik's cube. And permutation in cards, it's a second application, and in a pocket of card contains 62 cards, 52 cards, and each card contains 51 permutations. Therefore, for for total 6 for total 52 cards we are getting 8.06 into 10 to the power of 67 times of permutations. And the first the first half of the 20th century was a fallow period of study of the group theory in general, but interest in permutation groups was revived in the 1950s by H. Weiland, whose German lecture notes were reprinted as a finite permutation groups in 1964. Reference, the most of the topics I have referred from the Wikipedia and Math World, and the problems, all the problems are referred from the Elements of Group Theory for Physicists by A.W. Joshi. Thank you.